Right, welcome to the Parade Floats detailed presentation on the engineering and calculations we're asking you to do this week. Go ahead and make sure you're taking some notes. There might be some things that I say that aren't exactly written on the slides, but this video is available for your review throughout the entire week, so feel free to watch it as many times as need be. And always, just send Slowcaped an email if you'd like any further explanation or would like to learn a bit more about the topic. So, what are our two sources of energy for parade floats? In the introduction video, we talked about the two sources of energy we're going to be looking at for our systems, right? Gravitational potential energy and kinetic energy. Now we need to apply those to things that actually are in terms of a parade float. So for our gravitational potential energy, the mass of the float is going to be what we're looking at. And gotta love how I spelled float there. And our kinetic energy, when we're out in the parks, the largest contributor to the kinetic energy of the system is actually not going to be the movement of the float as it breaks and starts. It's actually going to be wind. So we're going to talk a little bit about wind, and then we're going to talk about a simplification we're going to make to take care of it. But I want you guys to get a brief understanding of how wind can affect your parade floats designs. So, wind force. The wind force load on your float is a function of wind speed and float face area. Now, if we kind of look over here at this graphic, and you can ignore some of the measurements and the bracing here, we just want to kind of look at this wall and the force of the wind. So what's happening when wind is blowing on your float, it is creating a force that is proportional to the area that it can blow on. So to think about this in a relatable way, when you are out in the freeway and you stick your hand out of the car window, if you stick your hand out on the car window such as that your palm is facing the direction of travel, your hand kind of gets blown back, right? You feel the force of the wind. But if you stick your hand out and your palm is parallel to the ground, then you kind of coast along and you can almost feel the lift force from the wind. So when your hand goes out and it has that big surface area of your palm for the wind to blow against, it gets blown back. Whereas opposed when it only just has the front little knuckle of your hand to blow on, you don't really get blown back as much. The same thing is true for our parade floats. So one of the important things that we would need to do if we were estimating the wind force load is to estimate your float face area, and this is often a limiting factor of parade float design. Now, typically, we would analyze at a wind speed of 50 miles per hour, as it's shown on the spreadsheet. We're going to talk a little bit about what the simplification is on the next slide here. So, we just talked about this wind force and everything, but it's not a mass, and it's not a velocity. So how can we translate this into our formula for kinetic energy, 1/2 mv squared? So this is something that we would actually worry about in more detailed applications on the park side. You talk to your meteorologist and get predictions for your max wind speeds and be looking at the effect of your park's geography as well as the potential wind tunnels that you set up with your buildings to figure out your max wind speed. Because that's kind of beyond the scope of what we want you guys to work on, we're going to make this assumption. Your deliverable will be the energy necessary to tip the float. Now, the engineers on site at your park are then ready to determine if the wind conditions are favorable for your float design. So we're not asking you to iterate on that, we're just asking you to report that number for us. So then, how do we calculate how much energy it takes to tip a parade float? Well, we're going to use the other component we talked about, gravitational potential energy. Now, we have some geometry here. On the left-hand side, let me turn on my laser pointer. On the left-hand side here, we have a parade float. Here are two sets of wheels, and this red circle here is what we call the center of mass. Now, the center of mass is a mathematical position where we could place all of the mass of the system and achieve essentially the same function for mass properties of the system. Typically, for parade floats, this is going to be just about centered between the two wheels as we see it is here, and a little bit lower than halfway up the parade float. This is often because the parade float chassis is very, very heavy compared to the scenic topping of the float. So in a true parade float, we could see a center of mass way down here because we have this super massive chassis and then just our scenic on top. So some of the dimensions here are exaggerated to make them easier to see. So in order to tip the parade float, what needs to happen is this center of mass needs to move all the way over so that it's on top of this wheel here. Now, this is the same for either side. We just chose to look as if it was tipping to the right. So, what does that look like? And we see that in the second picture here. In the second picture, the center of mass is directly above this tipping point wheel, and at this point, we're in very no good land. You can also see that we added a couple of different labels on here in lines. We've got these two lines here, H1 and H2, as they're labeled in their corresponding figures. And if you look, you'll see that these actually form a right triangle. Now that allows us to apply a little bit more geometry to the system. So we're going to invoke Pythagorean theorem. We have H1 and H2 here. And we're going to call this horizontal distance L. So your known parameters are going to be H1 and L. You're going to estimate the center of mass of your system. And like I said, you're going to position this pretty much halfway in between your wheels and maybe about a quarter of the way up your total design to account for the weight of the chassis. So now we have a way to know H1 and L, but we still need to know H2. So we're going to just really quick do a quick calculation using Pythagorean theorem to figure out H2, and then sub it into our formulas for gravitational potential energy. So once again, the gravitational potential energy, sometimes we call it U, is equal to mgh. In this case, H is H2 minus H1, because that's going to be the change in height of the center of mass. Now, by applying the Pythagorean theorem, we know that H2 is actually the square root of H1 squared plus L squared, where once again L is the horizontal distance from the wheel to the center of mass. So then, if we sub that back into our original formula, we have the potential energy is equal to mg quantity square root H1 squared plus L squared minus H1. And we see now that we have this all in terms of the parameters of our system, H1 and L. So now you can use the spreadsheet given to you to directly calculate your potential energy. And like I said earlier, that will then be processed by the engineer's park side to figure out if you are in acceptable conditions or not. So this has just kind of been a little bit of a learning experience to get you thinking about some engineering applications of dynamic entertainment set pieces. So once again, if you have any questions about this material, or if you would like to learn a little bit more about how that wind force might actually be dealt with, or any other factors of parade float design, please feel free to reach out to us.